Okay, and finally, just a quick note, just to, well, complete what we said. I hope you took time to do that by yourselves. If I'm considering the same example as before, so that function, and I want to study its differentiability, so let's do it as an exercise to see how we can apply again those theorems. So what do we have? Uh, Let me rewrite the definition. On or plus of e minus t sinus of xt dt. And I would like to be able to write that f prime of x is going to be the integral on or plus, again, of the derivative as a function of x of what's inside. So, well, I can write it with a straight d. Sorry about this. Okay, so d over dx of e minus t sinus of xt dt, which of course is, so I can't still write that this is a sure equality. This is still what we have to prove. I would like to be able to write that f prime of x is the integral on or plus of, so what should we get if we differentiate with respect to x, minus t plus d, e of minus t cosine of xt dt. Okay, so in order to prove that, what do we have to check? We have already checked about continuity and boundedness of these. We have that the partial derivative in x exists. And finally, we should find a dominating function. So for this partial derivative, for d over dx f of xt, okay, I should find a function g that does not depend on x and depends only on t, and that function g with should be integrable, and I have that for all x in R. I've got this. So again, this one is going to be fairly direct. I can put g of t is equal to t e minus t. We indeed have that the integral on R plus of t e minus t dt is bounded, so g is integrable, so simply because we don't have any problems in zeros, so problem could be at plus infinity, and we can bound above e of minus t by e of, sorry, for instance, that, well, that's all the stuffs we did last year, times 1 over t, let's make it 3 at least, for t large enough. Okay, and so which is 1 over t squared, and so that we get rid of the problem at infinity. Okay, right, so I have found a dominating function that is integrable, and then I can just directly, oh, sorry, sorry about this. Let's get back to our stuff. And so we can conclude from the theorem, by the theorem of differentiation of parameter dependent integrals, we can conclude that f prime of x is indeed equal to the integral on R of the derivative of the inner function, which we said was t e minus t cosine of xt dt. Okay, so this example was very straightforward because the bounding functions were obvious, but of course this is going to be the biggest challenge in examples in exercises implying this theorem. You will need to find a dominating function that is something that does not depend on the x variable, it depends only on the variable of integration, and that is integrable. Okay, so that's it. One of the nice applications exercise that we're going to do is I'm going to give you the complete text of that problem during the tutorial. Well, maybe I'll put it online before, and it's going to show existence and some properties of this function, the Euler gamma function. Okay, I don't know if you know. No, you can't see my pen here, but it's it's a function that, as you can see, is defined as by a parameter dependent integral. So that one, the integral between 0 and infinity, x to the power z minus 1 e minus x dx. So the integration is with respect to variable x, and the variable of the function is going to be the z. So we really have something like for parameter dependent integral. And this thing is that if you take integer values of for the z, for the gamma of z, you get the factorial. So it's a function that interpolates the factorial values for real numbers. Okay, so maybe I've got a nicer one. So if you look at that graph on the right, for integer values n is equal 1, 2, 3, etc., you've got the value of the gamma function is the n minus 1 factorial, and in between you just have a very smooth curve joining the dots. Okay, so that's the gamma function, and you're going to study this one. Okay, so see you very soon. Have a nice afternoon. Bye.